This is a basic video about blood gas interpretation. There are three objectives. The first objective is we want you to be able to describe the four acid-base disturbances. Then we want you to be able to define the normal values for pH, PCO2, or the partial pressure of carbon dioxide, and the normal value for bicarb. And finally, we'll present a simplified approach to interpreting the acid-base disturbances of blood gases. So, what are the acid-base disturbances? You can have a problem with the respiratory system, or you can have a problem with the metabolic system. And within each of those systems, you can have an acidosis or an alkalosis. This implies that there is a derangement in the acid-base status in the body, and the body is either more acidic or more alkalotic than it should be. For both a primary respiratory and a primary metabolic derangement, in both cases there can be compensation. This implies that if there is a problem with the lungs and there is a respiratory acidosis, for example, the body will use its kidneys to maintain base in order to compensate for the primary problem in the lungs. Alternatively, if there is a metabolic acidosis, for example, the body will increase its minute ventilation to get rid of carbon dioxide. This will in turn take the acid-base status of the body back to normal, or at least closer to normal. Now, you can have a primary respiratory or a primary metabolic acidosis, but you can also have a mixed respiratory and metabolic acidosis, meaning that both the respiratory system and the metabolic system are in an acidic state. Or you can have a mixed respiratory and metabolic alkalosis, meaning that both the respiratory system and the metabolic system are alkalotic. Now let's move on to the components of a blood gas. The first thing that you get in a blood gas is the pH. The normal pH of the body is 7.4, but it can range somewhere between 7.36 and 7.44. The next component you'll see is the partial pressure of carbon dioxide. The normal partial pressure of carbon dioxide is 40. It also has a range between 35 and 45 millimeters of mercury. Whenever you get a blood gas, you're also going to get a PO2, the partial pressure of oxygen. Now, the normal value of this depends on a lot of different factors, and we'll focus on that another time. The final component of a blood gas is the bicarbonate value. The normal bicarb value is 24, and it ranges between 20 and 28. Whenever you look at a resource, you'll see subtle differences in these normal values. Everyone agrees that a normal pH is 7.4, but the range of normal is subtly different. The same with the partial pressure of carbon dioxide and bicarb. So don't get hung up on the exact normal value, but think about it within a range. Now let's go to the third objective of this video, and that's developing a simplified approach to interpreting blood gases. So let's take a blood gas and interpret it. The pH of this blood gas is going to be 7.18. The partial pressure of carbon dioxide is going to be 30. The partial pressure of oxygen is going to be 92, and the bicarb is going to be 16. I'd like to take you through a 5-step approach to interpreting blood gases. The first is to examine the pH. Is it acidic, is it alkalotic, or is it normal? In this case, since it's lower than 7.36 and well below 7.4, the pH of this blood gas is an acid. Now you ask, does the partial pressure of carbon dioxide explain the pH, meaning that is the CO2 also in the acidic range? In this case, it's 30, which is not actually acidic at all. It's actually alkalotic because it's below 35. Remember, CO2 is an acid. The higher the CO2, the more acidic. The lower the CO2, the more alkalotic. The third step of examining a blood gas is, does the bicarb explain the pH? Well, 16 is lower than normal, meaning that it is in the acidic range. And therefore, since the bicarb is acidic, you can say that the pH is explained by the bicarb. So we have part of the interpretation of the blood gas already, and that is that this is a metabolic acidosis. The next step of interpreting a blood gas is to look for compensation. Remember, the body will try to take that primary derangement and make it as close to normal as it can by using either the respiratory system or the metabolic system and going in the opposite direction. In this case, since it's a metabolic acidosis, you look to the lungs and say, is there compensation within the lungs to take the blood gas back to normal? And since the CO2 is alkalotic, it's in the opposite direction of the pH. You'd have to say that there is some compensation. Therefore, you could say that this blood gas is a metabolic acidosis with respiratory compensation. Again, I looked at the pH. Is it acidic or is it alkalotic? Then I asked, does the CO2 explain the pH? In this case, it doesn't because the CO2 is alkaline in the alkalotic range. Then I looked at the bicarb and asked, does the bicarb explain the pH? And since the bicarb is in the acidic range, lower than normal, I could say, yes, there's a metabolic acidosis. And finally, I look at the other value, in this case, the CO2, and say, is the CO2 in the opposite direction of the primary pH, the primary problem? And since the CO2 is low, which indicates that it is alkalotic, you can say that there is compensation. There's actually a formula that can help you determine whether there's compensation when there's a metabolic acidosis. The question basically is, has the body increased minute ventilation to dump CO2? And we use something called the Winters formula to determine this. You can expect that the PCO2 will be equal to 1.5 times the bicarb plus 8. So let's use this blood gas as an example. In this case, the bicarb is 16, so 1.5 times 16 plus 8 is equal to 32. And there's always wiggle room in these things, so plus or minus 2. So given that this is a metabolic acidosis, you can use the Winters formula to predict the CO2. And if it falls within that range, you can say that there is true respiratory compensation. Here, again, the bicarb is 16 and our CO2 is 30. Our predicted CO2 is 32. Since it falls within range, there is a metabolic acidosis with respiratory compensation. Now let's think about the respiratory acidosis. It's the exact same thing. Has the kidney retained enough bicarb to compensate or come close to compensating for the respiratory acidosis? If you have a respiratory acidosis, meaning that the primary problem is that you have an elevated carbon dioxide, you should also see that the kidney is retaining bicarbonate to compensate for this, meaning that the bicarbonate should be greater than 24, and usually even greater than 28. Let's go back to the steps of interpreting a blood gas. The final step is to interpret the PO2. This is complex, but it goes along with a couple ideas here. The PO2 is only meaningful in an arterial blood gas. The truth is sometimes you'll see additional blood gases from the venous system or the capillary system. You can only measure the PO2 if it is the P little AO2 or the partial pressure of oxygen within the artery. It totally depends on the fraction of inspired oxygen, meaning that if you're on room air, your expected PO2 will be very different than if you're on 100% oxygen on a ventilator. In order to interpret the P little AO2, you have to use the alveolar arterial gradient to fully interpret it. And that's beyond what we're going to talk about today. What we can say is that for a healthy individual breathing room air at sea level, the expected P little AO2 is somewhere between 80 and 100 millimeters of mercury. So, in sum, we've talked about the 4 basic acid-base disturbances, talked about how they can each have compensation, and talked about how there can be a mixed acidosis or a mixed alkalosis. You now know the normal values for pH, PCO2, and bicarb, and we've presented a 5-step approach to interpreting blood gases.